Hello and welcome back. In this video we're working through an example where we're tasked with just sort of describing and investigating an object moving along this trajectory. The first thing I want to do with this is show that this is actually motion on a sphere. I want to show that r of t is always on a sphere centered at the origin. So one way I can do that, right, I want to show r of t lies on a sphere. That's my first goal, because that's going to inform me about velocity and acceleration. So show that this lies on a sphere. I know that a sphere is defined by having constant, constant distance from the origin, right? It's all the points that are the same distance from some fixed point. In this case, the origin. And so what I'll do is I'll find the magnitude of my position vector. So let's compute the magnitude of the position vector. It's square root of 3 squared cosine squared of t plus 5 squared sine squared of t plus 4 squared cosine squared of t. All right. Interesting. Here I'm going to get 9 cosine squared t. Here I'll get 16 cosine squared t. So that's going to be 25 cosine squared t. Combining my cosine squared t, so that's 25 cosine squared of t. And then I have 5 squared sine t. Oh, isn't that so nice how that works out? So notice the Pythagorean theorem, 3, 4, 5 triangle, right? It's one of our Pythagorean triples, and that's part of why this worked out so nicely. And so what do we get here? Cosine squared plus sine squared is 1. So I'll just have a 25 sitting in here. This is really just 25. Square root of that is 5. So yes, we have constant magnitude of position, which means this lies on a sphere centered at the origin with radius 5. So r of t on a sphere, radius 5, and at origin, centered at origin. Isn't that cool? That tells me that r and v should be orthogonal to each other, right? That was in the last video. This implies r and v are orthogonal. Let's go ahead and check that that really happens. So now I'm going to find velocity, v of t. So that'll be derivative of position. So this is what? Minus 3 sine t. This will be 5 cosine t. And this will be minus 4 sine t. To observe that r and v are orthogonal, we can take their dot product, r dot v. So this is going to be what? X multiplied by x. So this is what? Minus 9 cosine t sine t plus 25 sine t cosine t. And maybe if you're a step ahead of me, you can already see what's going to happen. Multiply these together, I'm going to get minus 16 cosine t sine t. Right, so minus 16 cosine t sine t minus 9, and then plus 25. Those perfectly balance out, and I get the 0 scalar for r dot v. So yes, check, r and v are actually orthogonal on this thing. So that's pretty cool. What's the speed of my object? Let's investigate that as well. What's the speed? For that, we want magnitude of the velocity. And so that's square root of velocity is here, so that's 9 sine squared t plus 25 cosine squared t plus 16 sine squared of t. And again, we see this happening. We get a velocity constant 5. So my velocity is constant. But my direction's changing, right? So I'm also going to find acceleration here. We've got some pretty good stuff going. I also want to find acceleration. Acceleration is, so take a derivative here, minus 3 cosine t. We have let's see, minus 5 sine of t. And here we have minus 4 cosine of t. Compare that to r. Wow, isn't that cool? Again, it's the minus of r, so it's still parallel to position. So that's pretty cool as well. And I think we've got just about as much as we can get out of this. Oh, here's one question I have for you. If we have, as I did in the last video, constant r, or constant magnitude of my position vector, we were able to show that r and v are orthogonal to each other. But I keep seeing this happening where r is parallel to a, or rather they're negatives of each other. Are you able to work with what the example I did in the last video and try and show that this holds for constant r? Might be something to try. All right, that's it for this video. I'll see you next time.